inviting me here, for bringing all of us here, and for the great weather we've had so far. So I've noticed when using a microphone, it's very easy to get distracted, put the microphone away, and then suddenly waking up everyone. So I hope I don't do this, but I cannot make any promises. So I want to talk about some joint work with Brian Kra, Florian Richter, and Donald Robertson, who are all in here. And by an amazing coincidence, Brian and Donald will speak after me. So we decided to collude and all talk about the same project in 3 different talks. So my talk is going to be the introduction. And the title of this conference is something like Nil Structures, Dynamics, Topological Dynamics, Ergodic Theory, and Combinatorics. So my talk is going to be the combinatorics in this title. So very nice. So as a prologue, I want to remind everyone what is Semeredis theorem. So Semeredis theorem states that if A is a set of natural numbers that has positive density, and let's use Banach density. So I can take any sequence of intervals whose lengths go to infinity. Okay, so if this is positive, then A contains arbitrarily long arithmetic progressions. So for this audience, I'll just say then A is AP rich. And so Semeredi proved this theorem in the 70s, but this statement was conjectured much earlier by Erdős and Turan. So just as a remark, this was conjectured, I don't know, in the 30s maybe, doesn't matter, by Erdős and Turan. And they made this conjecture because there was an earlier result due to van der Waerden, which gave the coloring version of this statement. So van der Waerden proved that I don't have space here to write everything. If we finitely color the natural numbers, one of the colors is AP rich. Okay, so if n is finitely colored, some Ci is AP rich. Okay, so this is how Ramsey theory seems to progress. There is a coloring result, then there's a conjecture of Erdős, and then there's a density version. So this is a bit of a prologue. I want to talk about something different, but it will follow the same regime. And it seems nowadays we could add an extra remark here, which is later tau gives some result about the primes, which is true for arithmetic progressions and is now true for what I want to talk about, which are subsets. So, so we need to go back to the origins of Ramsey theory, namely to Ramsey's theorem. Which, by the way, was proved almost the same time as van der Waerden's theorem. And it states that if not the natural numbers, but if pairs of natural numbers are colored, let me write it, are colored. So I want my colors to be symmetric. So let's pretend this makes sense. So if N2 is colored symmetrically, meaning the color of AB is the same as the color of BA, then there exists a set B in N, which is infinite, such that B times B is monochromatic, except that's false if I don't remove the diagonal. Now this is monochromatic. Okay, so really Ramsey's theorem is about coloring pairs of natural numbers, but we can think of it as coloring all ordered pairs, but making the color symmetric and then avoiding the diagonal because we want to consider graphs without loops. And so as immediate corollary of this theorem, which I don't think Ramsey ever written down, I don't know if anyone did at the time, it implies that if we color the natural numbers instead of pairs of natural numbers with finitely many colors, then there exists an infinite set B such that the sum set B plus B, and here I mean the restricted sum set, so I take every sum B1 plus B2, where B1 and B2 are elements of B, and they need to be distinct. So this sum set is monochromatic. It's monochromatic. Yeah, I hope it's clear. So monochromatic means contained entirely inside one of these CIs. Okay, so first question, why do we need to take the restricted sum set? Well, that's because in Ramsey's theorem, we had to remove the diagonal, and both results are false if we don't do that. So if I don't take the restricted sum set, there are counterexamples, and if you're very bored with the talk, you can take it as an exercise to find the counterexample. Second question, so we used Ramsey's theorem for graphs, and we got the sum of two sets. Could we not use Ramsey's theorem for hypergraphs? It turns out we could, so such a theorem exists, and as a corollary, we get that. So for every finite coloring of the natural numbers, and for every k now, there exists some infinite set B such that the sum of k copies of B, and again, it's the restricted sum set, so to be very precise, this is B1 plus BK, where all the BIs are in B, and let's say B1 strictly smaller than B2 and BK. So this k-fold sum set is monochromatic. So this follows already from Ramsey's theorem if you use the right version. But then you start to ask more questions. For every k, there is a set B. Now the set B depends on k, and the color of this configuration depends on k. And it's difficult to remove these dependencies just by quoting Ramsey's theorem. But it turns out that we can find a single set B that satisfies this for every k, and with the same color. And this is known nowadays as Hyndman's theorem. So if the natural numbers are finitely colored, there exists some infinite set B such that B plus B, B plus B plus B, and so on. This union is monochromatic. So all of these sums have the same color. Now, this thing is usually denoted as the finite sums of B. This is the set of all finite sums of B, and these things are called IP set. So I may use the words IP set during the talk. I mean one of these things. Okay, so to be clear, the Hyndman's theorem. Hyndman's theorem is much more sophisticated than any of these corollaries of Ramsey's theorem. Okay, so this checks the first item in our list. We have a coloring result about the fundamental configuration in additive combinatorics. Next step is Erdős will make a conjecture. So Erdős was thinking of how can we find the density version of Heinemann's theorem. And the first obvious observation is that not every set with positive density will contain an IP set, because the odd numbers have positive density. And if you have two numbers in B of the same parity, the sum will be even. But while the odd numbers are bad for IP sets, if we shift them, we get the even numbers, which are great for IP sets. So Erdős asked, could it be that every set of positive density has a shift which contains an IP set? It's not clear Erdős was thinking about Banach density, but it's all the same for us. There exists some shift T such that A minus T contains some finite sums of some infinite set B. Okay. And very shortly after the answer came out, it's no, it's not always true. And an example was constructed by Strauss. I can never remember how many S's it has. 2 S's? 2 total, yeah. So in fact, there are sets with the upper density arbitrarily close to 1, and no shift of these sets contains an IP set. So then Erdős became a bit more modest, and he thought, okay, maybe we cannot have, well, not maybe, we definitely cannot have a full IP set just by shifting an arbitrary set of positive density. But can we have maybe the first non-trivial element in this union, namely B plus B? So he made a conjecture. If A has positive density, it's not entirely clear what kind of density he meant, but let's say Banach density, then there exists some shift and some infinite set such that A minus T contains B plus B. Once again, the restriction, the sum set has to be restricted, otherwise there are counterexamples. And then Erdős made an even weaker conjecture, namely that A should contain the sum of two different sets, B and C. So let's call this conjecture 1, and then conjecture 2. So under the same assumptions, just shorten it a bit. Upper Banach density of A is positive, then exist infinite sets B and C, such that A contains the sum B plus C. So it's not it's not entirely obvious maybe, but the conjecture 1 implies conjecture 2. And this is not restricted. Exactly, right. So if we know conjecture 1, we get conjecture 2 by taking C to be just a shift of B. And then there's the restricted sum set issue, but you can just take two disjoint subsets of B and you can solve them. Okay, so these conjectures were open for a while, so no one knew how to solve them. So people naturally were focusing on the weaker one, conjecture 2. So let me tell you. The history there. So the first result was due to Nathanson. This was already in 1980. And he showed that under the same situation, then for every k, there exists a set B with k elements. So it's finite, but arbitrarily large. And some set C with positive density. You can say positive upper density, such that A contains B plus C. Nowadays, this result is an immediate corollary of Furstenberg correspondence principle and Poincare recurrence theorem. Well, I think that's what Nathanson did. The next development was due to Bergelsen. Thank you for reminding me. Shortly after, I don't know exactly the year, in the 80s. So Bergelsen was working on a different problem. He wrote down a lemma that was useful for some other purposes, but we could read off that lemma the following fact. If A has positive Banach density, there exists a set L whose density, and now its natural density, exists and is at least as much as the Banach density of A. And such that for any finite set B of L, there exists some set C. This set depends on B, but it has positive density as well. Maybe let's say Banach density to be safe, such that A contains B plus C. So the point here, we still are on a similar regime to Nathanson's result, where we have A containing B plus C, where B is finite, but arbitrarily large, and C has positive density. But here we don't just have some set B, we have many, many sets B. So any finite subset of this set L, which is in turn relatively large, will work. So more than the result itself, the proof of this result was then used pretty much in every subsequent result or the general idea. And the next development was due to 6 authors, none of which are here, so I'll just write their initials. It was the theorem of Mauro Di Nasso, Isaac Goldbring, Renlin Jean, Steve Leth, Martin Lupini, and Karl Malberg. And they proved 2 things. First, they show that if the upper Banach density of A is strictly larger than a half, then A contains B plus C. Now B and C are infinite sets. Both infinite. And then they proved something else at the end of the paper, which is less impressive, but it was more influential. So they introduced, they introduced the notion of weakly mixing set. But they weren't maybe the first to do it. But this notion of weakly mixing set comes naturally from ergodic theory, where we are very used to weakly mixing systems and even weakly mixing functions, as we saw yesterday in Sohail's talk. And so a weakly mixing set of natural numbers is a set that mimics the properties of a weakly mixing function in a dynamical system. So here's the definition. And I want to be a bit vague, but let's see if you catch me. So a set is weakly mixing if for every set B, and what do I want? I want A minus B to be A minus N to be independent from B most of the time. So I want the density of this intersection to be comparable to the product of the density. Comparable in the sense that the difference is smaller than epsilon. And I want this to happen for almost every N. So the set of N's for which this happens should have density 1. And what is epsilon? It's any positive number. So this is the definition of weakly mixing set. For any error epsilon you take, we look at when the shift of A by N is independent from B or almost independent, and there should be a full density set of N's for which this happens. Now, for this audience, this definition should sound very similar to saying that the indicator function of A, perhaps normalized, is U2 uniform. And this is almost true, not quite, but so we can think of it. Almost. The definition is a little bit vague. I'm not telling you exactly what the densities are. If I wanted to be specific, I need to start with a Foner sequence, pass to a subsequence where all the limits exist. The subsequence depends on B. So let's not be completely precise. So the important thing was not the definition. The important thing is what can we do with it. And so these 6 people, they proved that if a set A is weakly mixing and positive density, then it contains B plus C. And I want to show you the proof because it's very short and educates why uniformity seminorms have anything to do with some sets. So let me write it here. Theorem, why not? So if A is weakly mixing and has positive, say, Banach density, then, and in fact, A doesn't just contain B plus C, A contains B plus B, restricted for some infinite set B. Okay. So if I enumerate the set B, if I let B be the image of some sequence Bn and N, where B is increasing. So then the conclusion that A contains B plus B, I didn't stress, by the way, there's no shift needed here. If the set is weakly mixing, it will not have any local obstruction, so I don't need to even take a shift. And so the statement that A contains B plus B is equivalent to the statement that for every N and M, let's say N smaller than M, B of N plus B of M is in A. And this is in turn equivalent to the statement that for every M, B of M is in the intersection of A minus B of N for all N smaller than M. And so we will prove this result by constructing this sequence B of N inductively. And at every time I want to choose B of M, I just need to check finitely many things. And the strategy of the proof is to make sure that this set is, well, first of all, non-empty, but actually has positive density, which is something we can ensure using the weakly mixing property. So here's how it goes. So take B of 1 in N, pretty much arbitrary. We can, right, so let B1 be this shift. So B1 has positive density because it has the same density as A. So I can use the definition of weakly mixing to conclude that this set of B's for which the density of A intersection B1 is positive, that's all I care, that this set has density 1 by the definition of A being a weakly mixing set. Except I didn't write the correct thing. A minus B. Okay, because this set has positive density, it will intersect this other set. Sorry, this set has full density, so it will intersect this other set that has positive density. This will be even more convincing if here I don't use upper Banach density, but lower Banach density. Okay, so once again, this set has positive full lower Banach density. This set has positive upper Banach density, so they must intersect. So I can choose my second element in this intersection. And when I do, B2 is in B1. So in particular, B2 plus B1 is in A. So I satisfy my star property up to B2. And the fact that this holds will help me now to choose B3. So what happens, I will call this set B2. So B1, and then I take A minus B of 2. You read that all the way up there? Very good eyesight. Okay, so B2 has positive. Oh, yeah. B2 is B1 intersection A minus B of 2. B of 2 is this element. Right, and so because of this property, the density of B2 is positive. All right. Now we do the same thing. I take B3 in the set of B's where the density of A minus B intersects B2 is positive. All right, the set of B's that satisfy this has full density. So I can intersect with B2 that had positive density. Because B3 is in B2, you can unravel the definitions, check that this is satisfied, and that I can keep going for the next step. So we just iterate this, and that's the end of the proof. Yeah, so any questions there? No, so that's a good question. So this means not that the system is weakly mixing, but that the set that comes out of the correspondence principle, its indicator function is a weakly mixing function. In the usual sense of Sohail gave us yesterday. Another excellent question. Another excellent question. So if the system was weakly mixing, we could run it and get an IP set inside of A. And the next thing I wanted to say is we assumed here U2 uniformity. If we assumed, say, U3 uniformity, we could run the exact same proof and we would get B plus B plus B. So uniform in the semi-norm uniform. Right. So here. Okay, so continuing with the story, so then we proved the first Erdős conjecture. So this was joint work with Florian and Donald. This appeared, I think, in 2019. I'll just write it like this. If A has positive Banach density, then A contains B plus C. B and C are infinite sets. And our argument somehow combined this idea with the dual fact that if A is a Bohr set, then it's quite simple to find B plus C inside of A. The difficulty was to unite these two into a single proof. But once we had it, we got the feeling that by just upgrading U2 uniformity to higher uniformity, we should be able to prove the following statement that we made into a conjecture in the same paper. If A has positive density, then for every K, there exists sets B1 up to Bk, such that all infinite, say, such that the sum is inside. So 1 year later, Bernard Host gave another proof of that theorem. In fact, he told us how to write our proof. He wrote it using ergodic theory, which is what we should have done in the first place. And because you have ergodic theory, you can use a lot of simplifications to our argument. So it was shortened from 50 pages to 10. So Host, so he gave an ergodic proof. And as a bonus, in the same paper, he built an example of a set A, which has positive density. So it must contain B plus C. But both of the sets B and C, which are infinite, must have 0 Banach density. So he showed that there exists a set A with positive Banach density, such that whenever A contains B plus C, the Banach densities of A and B and C are both 0. Here. Oh, that's a good question. No, so yeah, so the example of Host is a weak mixing set A. Yes, if properly defined. Right, so we cannot just hope to bootstrap the theorem and get this stronger version. So then, last year, we finally proved that conjecture in joint work now with Brian Akra and Florian and Donald. So let me state it as a theorem. And our proof, really what we did, we needed a new proof of our first result of B plus C. And so we did find a new proof, different from our original proof, different from Host's proof, and different in a concrete sense, or an explicit sense, that we don't see in the combinatorics, but we see in the dynamics. Right, I didn't say anything about the dynamics. these proofs are, they use ergodic theory, they use topological dynamics, and this last one uses Nil's structures. It's very appropriate for this conference, and I'm sure you'll hear more about the proof in the next two talks. So I will say nothing more about the proof. The point is, when we got a new proof of that result, that new proof extrapolated, not effortlessly, but with the existing Nil theory more or less effortlessly, to give a proof of this full result. And then we looked at what we had, and we started thinking about the first conjecture of Erdős. And we realized that the technology we had developed to prove this theorem can also be used to prove the first, verify the first conjecture of Erdős. So then we proved that as well. Then exists infinite set B. And some shift T in N such that A minus T contains B plus B. Okay. So now that this is out of the way, we can focus on the real objective, which is to find a density version of Feynman's theorem. This is what Erdős wanted to find. And so we cleared the first level. And so now we're thinking, what is next? And so with the same technology of this paper, we can actually get something a little bit stronger. We can get that A minus T contains B and B plus B. We didn't quite write this in the paper for some reason, but we can do it. And so the next question is very easily suggested by this. And we get, can we keep going? Now we cannot go forever because Strauss tells us we need to stop at some point, but maybe we can go up to any finite k. We are led to this conjecture. If A has positive upper Banach density, then there exists some T and some infinite set. Moment. Yeah, I need to give myself a K in here. And for every K, there exists a T, which may depend on K. And there exists some B infinite, which also depends on K, such that A minus T contains B, B plus B, triple sum of B, all the way up to the K-fold sum of B. And in some sense, this is the best we can hope for. Again, we cannot go all the way to infinity because that would be an IP set. Now, there's an issue with this, not an issue, but we still don't know how to get B plus B plus B inside the shift of A. So I guess there are two conjectures here. The weaker one is get B plus B plus B. The stronger one is can we get all the way up to K? It is possible that the technology we developed to prove these results can be can lead to a solution to this, but yeah, we would need more work. I'm almost out of time, but let me just mention one final conjecture related to all of this. I already alluded to this at the beginning, and the conjecture is that the primes contain B plus C. So this was proved by Granville, conditional on the Hardy-Littlewood tuples conjecture, for those who know what that means. It's a widely believed conjecture in number theory, which greatly generalizes the twin prime theorem. And that was more or less the the status of these until earlier this year. And I'll just mention theorem of Tau and Ziegler. They showed that there exist two sequences B and C such that B of n plus C of m is a prime whenever n is smaller than m. So in a way, they get half of a sum set in the primes. And so they combine, I already erased, but the result of Bergelsen I mentioned earlier with some very deep number theoretic input to get this result. Okay, so I'll just stop by saying there are a lot of other natural interesting questions in this area. We think this is just the beginning of the study of infinite arithmetic configurations in sets of positive density. And maybe I can say that there will be a survey, hopefully soon, listing some of these natural problems. Yeah, so I'll stop there. Thank you. Should I repeat everything? So, okay, so I said that conditional on hard-delta tuples conjecture, we know that the primes contain, or primes minus one, rather contain this configuration up to a finite k. And we also know they don't contain an IP set. So I don't know if I know any result. We vaguely conjecture that they should have size log n. Maybe because it's the best lower bound we can get for it. So I haven't thought too much about it. Oh, so the question. No. If A has positive density, what's the best growth rate we can get here on B and C? In a finitistic sense, we can get the bound log n just by using. Yeah. Here I don't have any lower bound in that. So the kernelity of B up to n should be about log n, but I have no, I claim no result. Yeah. That's just not. It's divisibility. We can take it as an exercise.